Right.
Okay. I think I have some things that will be helpful here.
Since I get the general basic concept and how it looks on a graph,
Okay.
just not exactly how.
Okay. The process of actually finding the zeros with the iterative process is really pretty straightforward.
Okay.
Okay. You make a guess on the first zero. So you guess some x sub 1. Okay. And then the next zero is equal to your first guess plus the function evaluated at your first guess divided by the first derivative of the function evaluated at your first guess.
Okay.
Okay? So if you do this process, you will narrow in on the actual zero. I don't have a real good photograph here, but this function here is x squared minus 2.
Right.
And we know that the zero is square root of 2, right?
Right.
But let's say we made a first guess of 1. Well, the assumption of Newton's method is that the derivative, the slope, the slope at that point is going to point towards the actual zero. And in this particular case, you can see that it does. If we take the slope at that incorrect guess and find the x-intercept, it's right there, very, very close to 0, or to the actual intercept.
Okay.
And now if we use this as our next guess and take the derivative evaluated there and figure out where that intersects the x-axis, we gradually hone in on the actual zero. And you do it in an amazingly few amount of steps. In other words, in this particular problem here, our first guess was considerably off. We guessed 1.
Right.
And the actual number is 1.414214. Okay?
Right.
And with only 3 iterations, we get 1.414216, which is within 2 millionths of the actual zero. So this process works unbelievably well as an approximation for most functions. There are some functions where it does not hone in on the zero. It keeps bouncing back and forth and never does find the zero.
Okay.
Okay, and there's a test you can use for determining whether it's going to converge on the actual zero or whether it will not.
Okay.
Do you want to go through an example of one?
Yes, please.
All right, let's go through a different one here. Let's consider a function that it's not so easy to find the zero of.
Okay.
Just a little bit of math history. It was only 300 years ago that somebody figured out how to algebraically find the zero of this function. By using something called a solution by radicals, which is not even taught until you get into college now.
Lovely.
And you can use that solution by radicals to solve cubics and quartics. But 100 years ago, a couple of mathematicians proved that you cannot solve quintics that way. And quintics and higher are, I'm not sure how you solve them. There's not like a quadratic formula for solving them. There's not like a quadratic formula for solving this cubic. But there is this thing called the solution by radicals that will produce a solution. It looks awfully strange. You end up with radicals inside of radicals as your solution. But you can still do it. Okay? So Newton's method was extremely valuable because they didn't have a good way of finding zeros of certain polynomials. All right. So let's guess at a solution here, and the best way to guess at your initial solution is to get an approximate graph of the thing, and that's an approximate graph of this function.
Okay.
So if I were going to guess at an initial solution, I would say x sub 1 is equal to minus 1.2.
Okay.
Okay. Now, let's go through the calculations here. So, x sub n, our first guess, is minus 1.2. Well, we need, since our formula for the next guess is a function of the first guess and the function evaluated and the derivative of the function evaluated at that first guess, then I need f of x sub n and f prime of x sub n.
Okay.
So let's figure out f of x, f of minus 1.2, since that was x sub n. Turns out that that's 0.184. I'll save us some time.
Okay.
Now, if we take f prime of x, it's easy enough to take the derivative of that and evaluate it at that first guess. We get 5.24. Okay? So, our next guess is a function of x sub n, f of x sub n, and f prime of x sub n, which we have right here, those three values.
Right.
Okay? So, our second guess, x sub 2, is going to be minus 1.2 minus 0.184 divided by 5.24. And that is equal to negative 1.23511. All right? So that is a better guess than our first guess. In other words,
right,
we're honing in on the solution with just a second iteration. Okay? So now we have over here on the left, I'm going to say x sub 2 equals minus 1.23511. So what is x sub 3 going to be? Well, before I get x sub 3, I can only calculate x sub 3 if I know what f of x sub 2 and f prime of x sub 2 is. So let's write those. A table often helps here, but I'm not sure we absolutely need it. So f of x sub 2 equals minus 0.00771. F prime evaluated at this x sub 2 equals 5.68276. So my new best guess, I guess you would call it x sub 3. Now hold on a moment. Yeah. No, my first guess was minus 1.2, and after one iteration, x sub 2 was this. So this is going to be x sub 3, and it is equal to minus 1.23375, and if I do this in a calculator, that's the exact answer I get.
Okay.
So 2 iterations is all it needed to get the accuracy to within 1/100,000th of a decimal point.
Okay.
Okay? And no matter the complexity of the polynomial, in other words, I could have a 7th degree polynomial and it would work just as good. Maybe not in 2 iterations. I'm not quite sure about that, but my guess is that the higher degree of polynomial, the more iterations you would need to get it to within the accuracy that you want. And
Right.
the reason this only took 2 iterations to get high accuracy because it was a cubic. The other example was just a quadratic. It only took 2 iterations to get a very high degree of accuracy also.
Okay.
Now, there are some problems. Notice that each iteration is this formula over here. And also notice that in the denominator of that formula is f prime of x sub n. If that is ever equal to 0, you've got problems.
Okay.
Because you can't divide by 0. And if you were to divide by 0, this whole thing is going to be infinity, and then you really got problems. So it does not work if the first derivative is ever equal to 0. Notice that in our case, the first derivative here was equal to 5.24, and in the second iteration, the first derivative was equal to 5.68. If either of those numbers is ever 0, then this method isn't going to work.
Okay.
Another way that this method will not work is if you have a function like the following. Something like a logistic curve. This is actually f of x equal x to the 1/3. This is the cube root of x. Now, the reason this doesn't work unless, and this never works unless your first guess is 0. We can see that the zeros of this function are 0, and we can see algebraically that it's 0. But let's say we were to guess -1. Well, if you take the slope at -1, it points way over to here.
Right.
Well, if I go up to this point right here, my next iteration involves taking the slope at that point, and that point's way over here. Notice that we are not honing in on the 0. We're actually getting further and further away, although I suspect that it's only because the way I graphed it. I think we're going to be the same distance away each time. Because if I now go down to here, the function, and take that slope, it points to that maybe we do get further and further away. Yeah,
I suppose it depends.
It could get further and further away now that I look at it, because this slope flattens. As x goes to infinity, this slope gets closer and closer to 0, which means if you extend that tangent line all the way to the x-axis, it's further and further away from x equals 0. So with this particular function, Newton's method does not work at all. And it does not converge. If you have a function that Newton's method is going to work on, then each iteration will start to converge towards a number. And in that last problem where we had that cubic, and we got this as the answer, the next iteration gave us that also as an answer. Now, it might have varied in the 6th decimal place. Maybe that was a 7 and that was a 6. But there would be a number that each iteration would converge on. And that would be the exact 0 if you were to, do it in a calculator or by various other methods. And there is a formula that determines whether it's going to produce convergence or not. I don't know if you've been given this or this is unnecessarily complicated, but I'll tell you what it is anyway, even if you haven't learned it.
Okay.
If f times the second derivative, all divided by the first derivative squared, if the absolute value of that is less than 1, then it's going to converge.
Okay.
If it's not less than 1, then you can't tell. It may or may not converge. All right. That's all I got on Newton's method. In fact, when I got your message, I thought that you had spoken the message or typed it wrong. I thought that there was an error in there. And it was only when I looked in my book that this is actually called Newton-Raphson's method.
Right. Did I spell that wrong?
No, you spelled it perfect. I just didn't recognize it.
Oh, okay.
I thought it was.
Yeah,
I thought it was a misinterpretation.
No, but that is exactly what it is.
Voice to text or something like that. But yeah, it turns out that Newton is actually the one who discovered it, but he didn't publish it for 40 or 50 years after he first wrote about it. And in between, Raphson published it. So it became known as Newton-Raphson's method, but most of the books I have call it Newton's method.
Ah, I see. Yeah, for us, they definitely were like, it's Newton-Raphson method.
Oh, really? Okay.
Mm-hmm.
Yeah. Well, it's different in the fact that, oddly enough, most of the math principles that are named after people had nothing to do with that person. Like Euler's method was not founded by Euler, and I could go on and on and on about Pythagorean theorem was not founded by Pythagorean, and things like that. So this is particularly unusual, and the Newton's method was actually discovered by Newton, or Newton-Raphson also. Do you have a problem you want to try to work out?
No, not particularly. I just recall from first semester having particular trouble with this.
Okay, well, I think you can kind of see the concept.
Yeah, like the concept I understand, I just didn't quite get the mathematics.
In other words, if I guess that the 0 is at -2, well, if I look at the slope of the tangent line at -2, it's going to cross there, which is not the 0, but you can now use this and go up to the function and take the slope of that tangent line, and notice that it gets closer and closer. Now I can go down to here and take that point and take a new tangent line, and I'm honing in on the exact 0. And the actual process is really just as long as you know that x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n, mix and repeat, and you will get the 0, unless it's a particular weird function that doesn't, well, like that x to the 1/3. Doesn't work on that function because those tangent lines don't get you closer and closer to the 0. And in fact, it doesn't matter what your first guess is on that. You will never get the 0 unless your first guess is 0 on that particular x to the 1/3 function.
Right.
So I'm curious, that problem you gave me right before we ended our last on optimization problem, I spent at least 3 hours thinking about that problem over the last week. Well, it's a very interesting problem, regardless of whether you gave it to me exactly the way it was given to you or not.
Actually, I came up with it.
It's the same shadow regardless of where you're at on the cube, right? As long as you stay inside the circumference of the cube, the shadow is the same, no matter where you're at.
The same area?
That's what I came up with. In other words, if you're looking at it from the top, remember I thought that would be the optimum position, because that produces a shadow like this.
Right.
But then I examined a couple of other positions, like that position, which produces a shadow like that, which is the same area. I did all the geometry involved, and placing, obviously if the flashlight is placed out there, it increases the size of the shadow. So there's no way the flashlight can be outside the perimeter of the cube. And clearly, if that produces the same area, then so does that, so does that, and so does that. And logically doing the math, that that also produces the same area. So as long as you are inside the perimeter of that cube, you get exactly the same size shadow.
Huh.
Now,
That's not what I got when I did
well,
it.
I may have done it wrong. I did it, and there was a lot of arithmetic involved, and I was shocked that I came up with exactly the same numbers when I tested all of these places. But I also made some assumptions that I'm not sure were correct. I assumed that the flashlight was tethered to the center of the top face as opposed to the center of the cube.
I did the very center of the cube.
Okay, I wasn't sure.
Yeah, since I figured that out by using, I figured out the angles.
Okay.
Actually what I had 2 blocks, 7 centimeter by 7 centimeter by 3.5 centimeters.
Okay.
And I just put them next to each other. And then on one side of the block, I figured out the angles on the block itself, say by, let's say, for example, a tangent of 15.
Right. That's
Then
what I mean. Yes. And in other words, when you look at it from a plane that's orthogonal to this view, you can figure out all of the geometry as to where the shadow ends. So where did you end up? What was the optimum when you did it? Was it right in the middle?
Yeah. However, the shadows were a little bit weird, since I wasn't exactly on center, and I couldn't do 0 degrees. The shadow was too large to do, since it ended up going past the paper that I was trying to record the shadows on.
Now, the one thing that I couldn't figure out was how to do this the mathematical way. In other words, the optimization way, which is where you have a function of 2 variables and you're able to convert it to a function of 1 variable. You take the derivative, set it equal to 0, and solve it. I couldn't figure out how to make, I know that if you set this up on a grid, whether it's that grid or whatever, your area is easy. It's x times y, or 2x times 2y. But I could never figure out how to make that function a function of 1 variable. In other words, you start out with your area as a function of x and y, and you don't have to necessarily turn it into a function of x or turn it into a function of y. You can actually turn it into a function of a 3rd variable, which is what I thought about doing, turning it into the function of the angle that the flashlight makes with the center. But there's 2 angles there also. In other words, there's this angle and there's this angle. So I ended up with 2 variables regardless of how I thought about it.
Yeah, that's why I tried to keep it on a 2-dimensional plane.
Yeah. Oh, so the problem was you could only move the flashlight on the x-axis.
Right. And that's what I did.
I actually came to that assumption that that had to be what the problem was. Because you notice how in high school calculus is called calculus of a single variable?
Right.
Well, I suspect that calculus of 2 variables is this problem, where you would be allowed to move the flashlight not only along the x-axis but also along the y-axis. I mean, isn't it possible that right there gives you the minimum shadow? We can certainly figure out what the shadow is when the flashlight is there, but maybe the minimum is right there or somewhere else, not on one of the edges of the cube. And in other words, to do a proper calculus analysis of this problem, you really would need to do it in 2 variables.
Right.
Doing it in 1 variable, I can do that. That's relatively easy.
Yeah, that's why I kept it on a two-dimensional plane.
Yeah.
I don't know enough calculus
Yeah,
in order to do
exactly.
it on.
Well, I don't either, to be honest with you. I don't know anybody in high school that takes calculus of two variables. Even Calc BC doesn't get into calculus of two variables. You don't really get that until you get to college. And it's been so long since I've been to college that I don't remember how to do the calculus of two variables. So I was a little surprised if that was going to be the problem that you had, was a two-variable. I mean, I know the IB program is advanced, but not that advanced.
Yeah, it's just like, well, hey, this is a little bit extreme.
Yeah, no, that's kind of what I thought too. But it is an interesting problem in that it
is.
Yeah.
And I had some interesting results. Of when I calculated it. However, the way that I calculated the area may have not been the most effective way, since what I did, I traced the outline shape of the shadow, which turned into it wasn't a square shadow. It seemed more like a trapezoid.
If I put a flashlight right there, it's going to strike that edge, and the edge shadow is going to be right there.
Right. And what happened was...
Right there. So the shadow is that area right there. And then, of course, you look from the other perpendicular to this, it ends up, if you look at it from a bird's eye view, you should get a shadow like that, as long as the flashlight is in the middle.
Right.
If the flashlight is at an edge, then you're going to get a shadow, obviously no shadow on this side, but you'd still get. And with my flashlight tethered to the top face, everything was the same area as long as that flashlight stayed above the top face of the cube. Now, if you tether it to the middle of the cube like you did, it's definitely going to make a difference. I'd have to go through and do all the geometry over again. But the geometry isn't that tough. In other words, this angle theta here is the same as that angle theta there.
Right.
And so it's easy enough to calculate that distance and determine the area of the shadow. All right. Diana, I will let you go, and I will talk to you next Thursday.
All right.
Okay?
Thank you.
All right. Have a good week.
All right. You too.
Bye-bye.